Learning objective 2. There are three forms of these production functions we're going to be using. The first form is linear, and linear is a line. And this equation should look very familiar to you. It's quantity equals A times K plus B L. Now this one is not our normal format because we're stating quantity as a function of capital and labor. In this case, the marginal product is quite straightforward. For the marginal product of capital, it's simply the coefficient in front of capital. It's alpha. In the area of the marginal product of labor, it is the factor or the coefficient in front of the factor for L, which is B. The average product, as we did previously, is you take the total production and you divide it by whatever input variable you're examining. So the average product of labor, take the total divided by labor. The average product of capital, take the total divided by capital. And notice that the marginal product in this case, which is the slope again, is the same for any point. Why? It's a line. So there is a constant marginal product in this condition. The second form we'll look at is the Leontier. And this one is a very unusual relationship such that there is a very rigid fixed proportion where we need a certain proportion of capital to labor. And the graph you see here with all these lines, these L's, show that if we're at this point, we're going to be able to do quantity 1. But look what happens. If we keep adding labor, we get no more quantity because we're still on quantity 1. If we're at this point and we add more capital, same thing. We get no more production. So the optimal point is at these elbows, right at the very edges of these intersections. That is the optimal point as we go from quantity 1 to quantity 2 to quantity 3. So this is a very unique circumstance where we have a specified combination of capital and labor required to make a certain amount of output. The third form that we're going to look at is Cobb-Douglas. And this one has a curve to it, which is more realistic. And it shows that there's a function where capital raised to the power of A times labor raised to the power of B yields the quantity that is produced from that combination of labor and capital. So it graphs looks like this. Of course, the factors change and the graph will look different, but the shape is what I'm going to indicate, which shows this relationship where the marginal product here is quite dramatic, whereas the marginal product here is not, right? So here, the marginal product of capital is alpha times K raised to the power of A minus 1 times L raised to the power of B. And the marginal product of labor is B of capital raised to the power of A and L raised to the power of B minus 1. This should look familiar to you since you're all calculus experts now. If we take the derivative of this expression here with respect to capital, we take the alpha, put it in front, the capital, bring that value or a variable in, and then the new power is A minus 1. Then the other number stays constant because we're only varying capital in this first case, so we leave L alone, L to the raised to the power of B. Now, if we do the other variable, marginal product of labor, now we hold this factor constant, which is K to the power of A, and B is the coefficient. We carry that forward, and L raised to the power of B minus 1, right? So these two expressions are simply the first derivative of this expression with respect to K for this one and L for that one, all right? So hopefully this is starting to feel more comfortable to you. Average product is the easy one. What is the total production divided by K and the total production divided by L?